due to my business trip to Greece, this lecture 3 is pre-recorded. Sorry for this recorded video, and thank you for your kind understanding. Okay, so now let's go to our uh, previous lecture contents. In the previous lecture, in lecture 2, we have thought about a CMOS inverter. So in this case, we have ground and VDD, and by changing the input voltage, actually we can control also output voltage. That was done by this simple circuit called as the CMOS inverter. Here we have P MOSFET, and here we have N MOSFET, and they are reacting in the opposite way. If we apply positive bias much higher than the than threshold voltage, then this N MOSFET can be activated. At the same time, this P MOSFET becomes deactivated. So only one of them is turned on and the other is turned off. That's the reason why our output voltage is well selected between this ground level 0 voltage and VDD. So in order to calculate its voltage transfer curve, so we had tried to solve a certain equation. What was the equation? The equation was the sum of N MOSFET drain current and P MOSFET drain current should vanish. It was applied to the node shown here. This node, the output voltage node, is connected to the drain of our N MOSFET and also drain of our P MOSFET. So this is the predefined direction of our P MOSFET drain current, and this is a predefined direction of our N MOSFET drain current. So both of them are escaping from our out node. So sum of these two currents should vanish, and this is nothing but Kirchhoff's current law. We must obey this simple relation. So of course, this N MOSFET drain current and P MOSFET drain current are function of input voltage and output voltage, and input voltage and output voltage. And also we assume that the value of input voltage is given as our input parameter. Yes, for example, 0.5 volt, 0.6 volt. This value is just given, and the only remaining unknown variable is output voltage. So we wanted to solve an equation for the out value. Previously, in order to solve this equation, we have used a heuristic trial and error approach. What was it? Just try one output voltage. Of course, there is no guarantee that this is the real solution. If we have the values like this, lower than 0, it means that our N MOSFET drain current is smaller than that of P MOSFET current. So therefore, we wanted to increase V out. If this is the opposite case, for example, if this is the positive, then it means that N MOSFET current is in its absolute sense, it is that of P MOSFET drain current. So we can reduce this V out value. Then how much the change should be? So there we have used a heuristic value just to make a certain guess and check the result of that voltage changes. So of course it worked. However, we wanted to make a better guess for next changing for our V out value. What will be a better way and systematical way to update our V out value? We will study that method in today's lecture. So this is just a repeat of my previous explanation. So at the output node, we must solve this KCL, Kirchhoff's current law. At a certain circuit node, sum of all branch current should be 0 when we unify the direction of a branch current. So in this case, both of our N MOSFET current and P MOSFET current are escaping from our node. So their notation is unified. So simply we have a vanishing current here. Please note that this problem becomes complicated only because these functions are nonlinear functions. So now let's think about this way. This is just a given number and this is a given number. However, even in that case, our MOSFET drain current is a nonlinear function of voltage. And a PMOSFET drain current is also a nonlinear function of output voltage. So as I shown here, written here, the nonlinearity is the root cause of our difficulties. Is it really the case? Yes. So I wanted to make the counter example. Consider instead of a nonlinear electronic element, please consider a linear system. So here, instead of a MOSFET, which is intrinsically nonlinear, we introduce two resistors and they are really linear. Even in this case, our KCL just reads exactly same as before. So, in this case, we have non-zero values just to balance between R1 current and R2 current. So, sorry about this different notation, but in this case, we have made a direction of current in this way, R1 current, and this is R2 current. So they are not unified in their current branch notation. So one is escaping and one is entering into the node. So that's the reason why we have a slightly different one. But essentially, they are the same as before. I mean that here the sum of current when their branch current notation is unified should be 0. So that occurs here once again. Then now let's try to solve this system analytically. In this case, here we have V out and branch current IR1 can be easily obtained by this expression. This is the result of Ohm's law, the equation for our resistors. And how about this IR2? So it can be easily obtained by the voltage difference divided by R2. In this case, VDD and V out. So here we have a VDD and V out. This one just simply states the voltage applied to our resistor. Then here you can see that VDD is regarded as a given value, for example 1.2 volt, and these resistances R1 and R2, they are all known value. So the solution can be found immediately analytically as shown here. So simply speaking, if we are considering linear circuit elements like registers, then problem becomes quite simple. However, if we consider nonlinear elements, then our KCL becomes quite complicated. So now let's try to remember our previous lecture L2. When input voltage was 0.5 and when we try to check the value of output value of 0.7, of course we had imbalance of terminal current. For example, MOSFET current was just 1.7 microamp. However, PMOSFET current was a minus 7.9 microamp. Certainly, mm, drain current is much weaker than PMOSFET current. MOSFET current is much weaker than PMOSFET current. So we have to increase our V out value. This is the right direction. However, by amount of 0.1 volt. Why 0.1 volt? This was just a heuristic. So, can we find a better way to update V out? Yes, we can find it, and the Newton method, the main topic of our today's lecture, will be the right choice for our situation. Okay, so I will try to explain it. So our approach looks like this. With an initial set of input voltage and output voltage. However, this is just a fixed number, so this is the only unknown variable we want to calculate. Then the KCL, Kirchhoff's current law, usually does not hold. So if you are quite much lucky, then you can find the solution in your first trial. However, in general case, maybe your V out is not close enough to the real solution. So I guess that maybe your first trial was not that successful. So yes, in this case, it was a failure of our solution procedure. However, we wanted to improve this situation by adding correction to our V out, our solution. Now we believe that this is a much better solution. And when we insert this sum of the current value and update value, then it satisfies the KCL. If it is really the case, then we will have this expression. Sum of N MOSFET current and P MOSFET current vanishes with this updated solution. So now we wanted to find an equation for delta V out, the update. Unfortunately, this equation itself is as complicated as the original one as shown here. So there is no improvement or no easiness of solution procedure. So therefore, unfortunately, we must introduce a certain approximation. So up to now, there was no approximation, but we need a good enough reasonable approximation. So that will be the key step. Linear approximation is the one we have to employ in this case. This is really important, and this is the key step toward a practical method. So in principle, if you can solve this equation, then you will get the perfect delta V out. However, it is not possible to solve this equation easily. So instead of that, we wanted to make certain simplification. Although this is the exact one, difficult to solve. So an approximate equation is built by adopting the by adopting the linear approximation. So each term here and here, each of them is approximated with linear approximation. The way is quite straightforward. So first take the current value, and under the, the assumption of a smallness of this delta V out, this one is regarded as a small variation, then we can introduce this first order derivative and the sum of these two terms just to give us the first order Taylor expansion. The first term is expressed in that way, and of course we have another term. Second term is expressed as this one. So we have a constant term and linear term with respect to delta V out, the update value. Okay, then what is the difference between the original exact equation and this simplified approximate equation? The point is, although this equation contains non-linearity, however, this approximated equation doesn't have any non-linearity. This one, they are linear to our unknown variable delta V out, and they are just constant. So this system or this equation can be solved quite easily by using our simple calculator. That is the big difference between these two cases. Of course, I have to say that although we can calculate delta V out, but this is not a correct or rigorous equation. This is just an approximate equation. So the solution of this approximate equation, this delta V out, does not match to the exact value shown here. So maybe we have to improve our solution again and again. That's the reason why we have to do some iterations. But anyway, it's okay. So once we have this approximate equation, then as I told you before, now we can make this manipulation. Our unknown variable contains a certain coefficient in it, and they are related with first derivative of our nonlinear functions. And here we have the constant term, and this constant term is obtained by the drain currents for N MOSFET and P MOSFET without having any uh, changing in our output voltage. So how can we calculate this number? Since we know already input voltage and output voltage as our temporal solution, we can just evaluate it. And how about this one? Since we know V in and V out, then calculation of this PMOS drain current is straightforward. So this is related with the value of IDN and IDP. It's okay. It is already available. The thing which is not available right now is this one. Here we have some terms related with the partial derivative of our drain current with respect to V out. Also, drain current derived with respect to V out. So we have to implement it. Then, of course, in order to calculate this derivative, we must first of all identify the functional form of IDN on V out and also IDP on V out. But fortunately, these terms are known to us. already we have, although that is divided into several operational regions. However, but anyway, for a given value of V in and V out, we know complete expression for these two functions. So we spending a little bit more implementational effort, we can also get these derivatives values. So let me just show you a case study. For example, let's assume that our MOSFETs are in the saturation region. So in this case, for example, the expression for MOSFET drain current is shown here, and the expression for PMOSFET drain current is written in this form. Wow, it looks quite complicated. However, as you can see, it has a certain dependence on V out, and also here it has the dependence on V out. So taking the partial derivative with respect to V out is quite much straightforward. So, for example, you can easily do it in this way. So much easier than we expected, because this is just a constant on our output voltage, and this is also constant on our output voltage. Only this term should be derived, and here derivation just gives us goes away, and only lambda n is the result of this derivation. So you can see that here lambda n, that's it for our uh, sensitivity calculation. So you can do it for uh, other device, PMOSFET. Also, I wanted to say that we can do similar jobs even in the linear region and in the cutoff region. So everything is quite much accessible to us. So let me just give you a numeric value. For example, it's like this. When V in equal to 0.5, this value has been used in our previous examples. So correct value of V out obtained from our repeated calculation was 1.157565 volt. So of course it has longer digits, but we'll just neglect it. And let's assume that we start from 1.1 volt, which is already quite close to the solution. Then when we evaluate the function value, here function value means that the sum of IDN and IDP, then it gives us minus 2.1 microamp. And the sensitivity, it is just means that derivative of our drain current with respect to the out value, and it gives us a certain value. So from these two numbers, so we can, for example, here, as shown here, we know the function value. Oh, sorry about that. I made a mistake. Not this one. We know the function value, and this is sensitivity. And this is a number, and this is another number, and by taking just a division operation, so we will get the update value. So the calculated update is just 0.06 something. So then now our solution becomes, yes, 1.164859. Yes. Then if we repeat this procedure once again, then calculated update becomes much smaller than the previous trial. Yes, previously it was 0.06, and now this one becomes 0.007. Yes, almost 10 times smaller than previous one. And when we repeat it once again, then now we have, oh, it looks quite good. We have 0.00008. I mean that it is already almost 100 times smaller than previous one. So it means that if we repeat this procedure following the Newton method, then our update value can reduce quite rapidly. So please remember our previous trial and error heuristic manner. At the time, we have used just 0.5 as a reduction factor for our steps. So why we took it 0.5? That was just a heuristic. For example, we can try also 0.1, or we can try 0.9. However, if this is too small, then sometimes the reduction step becomes too small too rapidly. After that, you should spend more time. And if it is too large, like 0.9, then we have to have many times of a back and forth and back and forth. So too many iterations. So, well, which one will give us the best value, or the smallest number of iterations to get a converged solution? Nobody knows. There is no predefined guarantee for the optimal value of this update or reduction factor for our voltage step. However, in the case of a Newton method, then this update or voltage change is automatically controlled by our algorithm, so it gives us quite a rapid reduction of update value. Oh, sounds great. So this method is, as I told you before, Newton method. And let me just give you more a formal introduction of this Newton method. Let's assume that we wanted to solve a certain equation. So there is a function of an unknown variable x, and we wanted to find out a certain x value which is satisfies this equation. And of course, we have an approximate solution x sub n. So why we have a subscript n? Usually it represents our nth trial or nth iteration. So iteration. So we wanted to have a good enough solution, but unfortunately, still our f over x sub n is not very close to 0. So in this case, how can we build a better solution x sub n plus 1, which one shows still doesn't have exact matching, but it's function evaluation. Here, this value is much smaller than that of our previous solution. That is our approach. So continuous improvement of our solution. If we repeat this approach again and again, and eventually we will get quite a good solution, quite a good numeric solution. That is our approach. So for that purpose, Newton method tells us just to evaluate the function value. Yes, it is quite easy and straightforward. And of course, if x sub n is the real solution, then this function value should vanish, but in practice, it does not. And another complication is, please try to evaluate the sensitivity of our function value with respect to the solution. So we can evaluate this one once we have the known form of f of x. Then by using these two numbers, function value and its sensitivity, and by taking this division and taking the negative sign, we can calculate the update value. And just to add this update value to our present value, and yes, now we have a better solution, x sub n plus 1. And with this n x sub n plus 1, we can also build x sub n plus 2, and also we can build x sub n plus 3, something like that. If we keep this way, then our solution will be improved and improved. And if we are satisfied a certain solution in a numeric sense, then we can stop the solution procedure. So it has a really good property, so I will explain it from now on, just to sketch its good property. Let's assume that the true solution of this equation f of x equal to 0 is denoted as alpha. So when you insert alpha into this argument position, then you have exact value of 0. However, your solution x sub n is a little bit different from alpha. So then by using the Taylor theorem, so we can write down in this way, starting from our approximate solution x sub n, the value at a different function value at different value of alpha can be represented as this function evaluated at x sub n and linear term, and finally second order term. Oh, if you remember correctly, the Taylor series shows us we have third order term, fourth order term, something like that. We have infinite series in order to have a general expression. However, the point is all of these higher order terms are just merged into this second order term by introducing a certain evaluation point. This is not exactly x sub n, but this is a certain value between x sub n and the correct solution alpha. So, well, what is this xi n? We have actually no idea. However, there exists a certain value. So now we assume that this value is more or less given. Then after simple manipulation, means that we just divide all of our equation with this term. So then we can make a simplification. So first of all, f of alpha equal to 0, because we have assumed that this alpha is special, the true solution, so that is gone. And now we have the terms related with f over df dx. This is the one we have. And here we have xn comes from this point, and alpha comes from this one. And also we have this right hand terms comes from this expression. So there is no magic. We can just make a simple manipulation. However, the point is, without any further approximation, now we can find that this is corresponding to actually this one up to this negative sign. This term can be identified as our update delta x. So what is the sum of xn plus delta x? This one was regarded as the next improved solution x sub n plus 1. So as you can see that this equation can be just summarized in this way. What is it? The difference between our next approximate solution and the real solution. This is actually the error of our n plus 1's iteration. And this quantity is corresponding to the error of our nth iteration. So it simply means that the error of our previous round or iteration is just doubled and uh, um, and now it becomes the next iteration's error. For example, if our previous error level was 0.01, then maybe we can expect next error level just around 0.0001 because it is proportional to the square of our previous error level. So that is usually called as a quadratic convergence. And if we draw typical convergence graphs, so the horizontal axis is iteration, and if the vertical uh, axis is corresponding to error of each iteration, then we can, and of course, take the log 10 of this error level, then we can find quite a typical inverted parabola. So here you can see. So this will be the one for nth iteration and n plus 1's iteration and n plus 2's iteration. Although this is just looks like a parabola, but for example, this one is corresponding to 0.1 and this one is corresponding to 0.01 and this is corresponding to 0.0001. So it means that once we are quite close to the solution, then Newton method can give us a quite rapid convergence into the alpha, the real solution. That is quite attractive. However, I wanted to give you a caution for practical application. The Newton method is quite sensitive to the temporal solution, approximate solution. Previously, we have talked about the starting uh, from 0.1 volt, but instead of that, let's assume that we are now starting from 1.0. Yes, still input voltage equal to 0.5. Then the update calculated from the exactly same manner just becomes 0.26 volt. What does it mean? So if we just directly apply this Newton method, then our next solution becomes 1.26 volt, which is even higher than VDD value. And usually that doesn't happen in our CMOS inverter. So obviously, so this one gives us a long result. So we must have certain limitation or regulation for our Newton method. So it is very important to start from a reasonable initial solution. Well, So if our solution is, for example, if our correct solution is 1.15, then it is good to start from 1.1 instead of starting from 1.0. But maybe students can ask me this question. Well, if we know the real solution, then there is no need for us to start this Newton iteration. So the correct value of our alpha is unknown. So although we try to our best, however, there is no guarantee that our initial value x sub n is quite close to the real one. There is no guarantee. Then what we have to do is sometimes the Newton method can generate such a quite high update vector or update value, which just to overcome the proper range of our unknown variables. So in this case, it should be damped. For example, without any further justification, we can limit the absolute update, for example, 0.1 volt. It means that although it says increase our output voltage, the solution 0.26 volt, but only increase only up to 1.1 volt. Yeah. So then next with this 1.1 volt, let's try to solve the problem. Also, when a certain update overcome the reasonable range of from 0 to VDD, then that is just came back to within this value. For example, if you have 0.05 volt as update of your solution, then, well, without any further consideration, you can just switch it back to 0 volt. Yes, this is just a safeguard for our Newton iterations. So the algorithm of Newton iteration itself is quite much straightforward. However, when you apply it to the realistic cases, then sometimes it fails or diverges. So we must introduce a certain safeguard for our Newton iteration, especially at the beginning of the Newton iteration phase. So at the beginning, it is far away from the realistic solution, so it becomes quite unstable. But if we restrict in that way, then it will eventually go to or approach to the realistic solution. Once it becomes quite close to the realistic solution, then even without this safeguard, it can approach or it can converge to the realistic solution quite rapidly. Okay, so I will give you the numeric example. So we are now trying to the same problem with the 10 to the minus 6 volt criterion and also start from 0.6 volt. And when we start from this one, of course, the actual update value by our Newton method is quite large. However, in this case, we just restrict it to 0.1 volt. It means that this is already damped. And here you can see that also even in this second, third, fourth, fifth case, we have the damped update. However, now we approach to 1.1 volt, then what was our previous algorithm? Our previous algorithm was just to heuristically try to solve 1.2 volt and found that, oh, already we are far too high to have the correct output value. After that, it comes back. But in this case, when you have a look at these 6 Newton iterations, but already you can find that the value is well adjusted, and here we have a certain value. After that, yes, after that, um, now we have a quite rapid convergence of our solution. For example, at the end of our iterations, and the update value was just 10 to the minus 8. So it was, please note that this was around 10 to the minus 2, and this is 10 to the minus 3, and it was 10 to the minus 5, and 10 to the minus 8. Rapid reduction of update value can be achieved, and you know that we need only 9 iterations to get the converged solution within 1 microvolt update. So Newton iterations is quite strong to get the solution, numerical solution of non-linear equations. So we will use this method for our entire semester. Actually, the multivariable version of this Newton method is called as the Newton-Raphson method, and we will use that one throughout our entire semester. Well, now you have homework. So since I'm not in Gwangju, so I will not be able to check your homework submission. So once again, the due is September 19th. Still you have a lot of time ahead. And please repeat our homework number 2 once again. However, once again, but in this case, solve the program with the Newton method we have studied in this lecture 3. So you will find that the Newton method is really powerful, and the number of iterations required to get the numeric solution can be reduced significantly. And also, it is quite robust with a certain safeguard. Okay, that will be the contents of our lecture 3, and quite similarly I will upload also lecture 4, and let's meet together once again on September 19th. Okay, thank you for your attention and have a nice day. Bye.